The Replication Threshold: How Matter Learned to Live. Episode 1: The Quiet Inheritance of Stone. Dr. James Ocampo was not the typical Hollywood version of a scientist. No wild hair, no frantic exclamations. He was reserved, meticulous, and deeply curious. His laboratory at the University of California, San Diego, UCSD, was perched on the edge of the biological sciences complex, replete with whitewashed corridors and endless glass windows. The lab's interior was neatly organized into stations, one for cell culturing, another for computational modeling, and a newly constructed corner dedicated to scanning tunneling microscopy and advanced spectroscopic tools. His quest was unusual for a mainstream research scientist working out of a biology department. Most of his colleagues were busy with epigenetics, CRISPR-based gene editing, or investigating the human microbiome's complexities. But James was drawn to a deeper question: the origin of life at the interface between inorganic and organic matter, an event that he believed held the key to understanding not just Earth's biology, but possibly all life throughout the cosmos. Morning routine and the unanswered question. Every morning began with an espresso and a review of the overnight data streams that his advanced AI software, BioSleuth, had generated. BioSleuth was no typical piece of code. It integrated quantum chemical calculations, molecular dynamics, and a deep neural network architecture trained on large-scale biochemical reaction databases. The system was designed to search for self-reinforcing catalytic pathways that could, in theory, emerge from purely inorganic substrates. A soft chime drew James's attention to his large, curved monitor. Data from the high-throughput scanning tunneling microscopy, STM, runs were ready. He'd programmed the STM to probe a variety of iron-sulfur mineral samples under simulated hydrothermal vent conditions: high temperature, high pressure, enriched in dissolved gases like hydrogen sulfide and carbon dioxide. In the earliest hours of Earth, many astrobiologists believed hydrothermal vents played a starring role in bridging the inorganic and organic worlds. He scrolled through the visualized data: spiky, three-dimensional landscapes of mineral surfaces, color-coded for electron density and potential binding sites. Something about the patterns of electron tunneling probabilities caught his eye. There were faint but repeating loci on these mineral surfaces that corresponded to stable, repeating attachments of certain small organic radicals. According to the AI's best predictions, these surfaces might not only facilitate the formation of short organic chains, but could, under the right conditions, harbor a type of proto-replication. The data was preliminary, but intriguing enough to raise the hairs on James's forearms. He sipped his espresso and sighed. This was the first hint of something that could be monumental, or a wild goose chase. He decided to forward the raw data to his friend and occasional collaborator, Dr. Sylvia Matsuda, a crystallographer in the chemistry department. If anyone could spot an artifact or confirm a novel pattern, it was Sylvia. A visitor from physics. Just as he rose from his seat, the lab door slid open with the whisper of brushed steel. Standing there in a crisp shirt and tie was Dr. Irving Chandler from the physics department, an old acquaintance known for a skeptical attitude toward fanciful biological leaps. Chandler, raising an eyebrow. "Morning, James. I heard from Sylvia that you might be onto something big in your experiments, something about self-assembling organic radicals on mineral lattices." James, smiling politely. "She's fast. I literally just sent her an email with the data. Let me guess, you want to see if the quantum calculations hold water?" Chandler: "Something like that. You know me. I'm always curious, but I need evidence. I worry that your AI might be pattern-matching noise. Remember last year's fiasco with the alleged room temperature superconductor data?" James: "BioSleuth is more specialized than that. I've validated the subroutines, especially the quantum chemical modules. They cross-check with real spectroscopy data, not just theoretical predictions." Chandler, nodding but unconvinced. "Maybe. Mind if I have a look at the raw logs? James, go right ahead. I'd love to hear any physics-based insight on the electron tunneling probabilities. Chandler seated himself at a neighboring workstation, scanning the logs with practiced eyes. Meanwhile, James prepped some slides from the mineral samples for optical inspection. The lab bustled with a quiet hum. Machines whirred, pipettes clicked, and the glow of monitors lit up the walls. Despite the calm, James felt a knot of excitement. He recalled the words of his graduate advisor long ago. In the search for life's origins, every piece of data can be a Rosetta Stone, or it can be worthless. You won't know until you dig deeper. Between inorganic and organic. 3 hours later, James convened a small, informal meeting at his lab bench with Chandler and a postdoc named Maya Fernandez, who specialized in computational chemistry. They hovered over a projection that displayed the STM scans in brilliant reds and blues. Maya, I've tested the reaction coordinates in silico. These organic radicals form stable attachments along specific edges of iron-sulfur clusters. The next step is seeing if they can polymerize. James, exactly. If they can form polypeptide-like chains, or even simpler carbon backbones that self-replicate, we'd have something that could be the earliest stepping stone toward life. Chandler, stroking his chin. All life ultimately relies on replicating molecules, DNA, RNA, or some other system. But that first replicator, scientists have long debated if it was an RNA world or something else. You're suggesting it might be an inorganic catalyzed precursor to an RNA world, or a parallel that might have preceded it. James, yes. If these mineral surfaces can orchestrate not just a single reaction, but a cascade, they could effectively template the formation of organic molecules that replicate, albeit clumsily. A hush fell over them. The idea was radical, but not entirely outside scientific discourse. The so-called iron-sulfur world hypothesis existed in the literature, positing that life began on the surfaces of iron-sulfur minerals. But James's findings, if they held up, might demonstrate a new mechanism by which replication could arise directly from inorganic scaffolds. Chandler, quietly. We need more proof than just STM images and computational modeling. James, naturally. I'm setting up a bench-scale experiment to simulate early Earth vent conditions. We'll see if the reaction can continue spontaneously over multiple generations. Maya, excited. This is huge. Think about the implications. If we can replicate this in a real environment, you might have found the missing link between chemistry and biology. James nodded, aware of the immense responsibility. A part of him was thrilled at the possibility that this line of research might rewrite Origin of Life textbooks. Another part feared the inevitable skepticism and the potential for error. Never trust preliminary data without thorough validation. That mantra was pinned above his desk. A detective-like pursuit. That night, James stayed in the lab until well past midnight, calibrating the new reaction chamber. In the fluorescent-lit stillness, he found himself drawn to the notion that he was doing detective work in the greatest mystery of all. How does life begin? Each clue was hidden in the atomic arrangements on these mineral surfaces, a puzzle locked in the deepest vaults of geological time. He typed a note in his digital log. June 14th, 10:48 p.m. Preliminary evidence for stable organic radical formation on iron-sulfur surfaces under simulated vent conditions. The replicative potential is as yet unknown. Testing next, continuous flow experiment to see if repeated cycles sustain or amplify the organic structures. If this works, it might represent a blueprint for how life's earliest precursors emerged. Feeling uncertain, but excited, must proceed carefully. With that, he shut down the overhead lights, leaving only the subdued glow of monitors and instrumentation. A wave of anticipation stirred in his stomach. In the morning, he thought, the real test begins. Episode 2. Gathering clues from the unlikely. High-pressure lab experiments. Early the next day, James enlisted help from two graduate students, Chris Patel and Rena Goldberg, to set up a continuous flow reactor, a pressurized cylinder designed to mimic the chemical environment of a mid-ocean ridge hydrothermal vent. The cylinder was lined with quartz windows so that spectroscopic lasers could monitor the reactions in real time. The plan was straightforward. Mix water, dissolved gases, CO2, H2S, and trace amounts of NH3, and small inorganic ions like Fe2+, Mg2+, and Ni2+. Pass the mixture through a heated, pressurized chamber containing the iron-sulfur mineral substrate. Monitor changes in the chemical composition via in situ Raman spectroscopy and mass spectrometry. If the minerals truly acted as catalysts, they might spark spontaneous formations of organic molecules. The ultimate test was whether any emergent structures would multiply over successive flows, akin to replication. Chris, double-checking the setup. Pressure stable at 250 bar, temperature at 120 degrees Celsius. We're good to start the flow. James, nodding. Let's begin. Keep an eye on the readouts every 15 minutes. Rena, you handle the spectroscopic data logs. He flipped a series of switches, activating pumps and heaters. The system hissed as high-pressure fluid coursed through the chamber. Over the next few hours, they watched the spectrometer lines dance across the screen. Carbon-hydrogen bonds started appearing in the spectra, faint at first, growing in intensity slowly. Rainer, eyes wide. It's not just single carbon-hydrogen peaks. We see patterns indicative of short-chain hydrocarbons. Look at this region. There's a shift that suggests possible sulfur-containing organic groups. James, like a thiol or a thioester group. That's exactly what some origin-of-life theories propose as an early metabolic handle. As time went on, the signals became more complex. Yet, was this random polymerization, or did something more organized begin to emerge? That was the million-dollar question. Enter Dr. Sylvia Matsuda. Just after lunch, Dr. Sylvia Matsuda arrived with a stack of her own data. Sylvia was a crystallographer specializing in X-ray diffraction and advanced electron microscopy. She'd examined the same type of iron-sulfur minerals under different conditions and had noticed unusual patterns of surface restructuring, almost as though the crystals themselves were adapting to repeated cycles of heating and cooling. Sylvia, handing over printouts. It's almost as if these mineral surfaces rearrange to form more reactive facets over time. I can't believe I'm saying that. Minerals aren't alive, but the data suggests that repeated thermal shocks and fluid flows create self-optimizing crystal edges. James. Self-optimizing? That's quite a phrase. You think the structure changes in a way that increasingly favors certain reactions? Sylvia. Yes. The XRD patterns show a slight shift indicating the formation of new planes that have higher catalytic activity. It's not random, it's directed by the conditions. They compared notes with the real-time data from the flow reactor. An emergent picture came into focus. As the mineral facets evolved, they fostered more stable bond formations of carbon and sulfur. The puzzle pieces were aligning to suggest that inorganic matter was not just passively hosting organic reactions, but dynamically enhancing the conditions that led to more complex chemistry. Chandler, who had drifted into the lab to eavesdrop, offered his cautious commentary. Chandler. This is reminiscent of a phenomenon in condensed matter physics, where iterative conditions lead to new stable phases. But here, the phases are shaping a biochemical potential. That's borderline incredible. James. Maybe not borderline. Perhaps these are the incremental steps that eventually lead to self-replication. Sylvia. Before we jump to replication, though, let's confirm we're seeing more than just random polymerization. A potential breakthrough. Over the next few days, the entire team worked almost non-stop. Each cycle of the reactor was carefully controlled, with subtle changes in temperature or pressure to mimic geological fluctuations. By the end of the week, the spectroscopic data showed an unmistakable pattern. Certain sulfur-rich organic molecules were not only forming consistently, but also increasing in concentration across cycles. It was as if each cycle seeded the next. Then came the bombshell result. BioSleuth flagged a set of reaction pathways indicating a rudimentary form of template-driven assembly. The analysis suggested that the sulfur-containing molecules arranged on the mineral surface could serve as a scaffold for further attachments of the same molecules, doubling each cycle. James, running a hand through his hair in disbelief. So, are you telling me these molecules are replicating by templating themselves on the surface? Maya. That's what the AI suggests. Each generation yields roughly double the attached molecules within the margin of experimental error. Sylvia, whispering, we might be looking at the earliest precursor to a self-replicating system on an inorganic substrate. They stared at the data in awed silence. If real, this was a scientific milestone. Yet, skepticism was also crucial. Chandler, for one, was not convinced. Chandler, I want to see the raw data. We have to ensure we're not misinterpreting random duplications or measurement artifacts as replication. James, agreed. Let's isolate the molecules and test them independently. Maybe we can see if they continue replicating off the mineral surface. The next step was clear. Separate the putative replicating sulfur organic complexes from the mineral substrate and see if they remain stable and capable of replication in a controlled environment. Detective work, indeed. In the following week, James felt like a detective analyzing a cryptic clue at a crime scene. The crime, in this analogy, was the spontaneous emergence of a system that shouldn't logically be alive, yet displayed one of life's fundamental properties: replication. He compiled reams of data, cross-checking them with standard references for known molecules. Many of the peaks in the mass spectrometry data didn't match anything in the existing databases. That alone was breathtaking, novel organic structures forming spontaneously, possibly bridging the inorganic-organic divide. The scientific rumor mill at UCSD began to hum. Whispers circulated. Could it be that Dr. Ocampo and his group discovered the holy grail of origin of life research? James knew better than to fan the flames prematurely. He needed airtight evidence. Meanwhile, departmental politics emerged. Some faculty were excited, others were openly critical. The phone in James's office rang incessantly. One evening, he found himself ignoring calls, lost in the data streams on his monitor. Then a quiet knock on the door startled him. It was Dr. Eleanor Kim, a visiting scholar from MIT, known for her work on quantum biology. Elena. May I come in? James. Of course. Please. Have a seat. She perched on the edge of a chair, eyeing the scattered piles of printouts. Elena. I've been hearing all sorts of rumors. Something about replicating molecules on mineral surfaces. I'm intrigued because my group studies quantum effects in enzyme catalysis. Could quantum tunneling be playing a role here in your system? James. Possibly. The binding energy changes we're seeing might involve tunneling. Some of these reactions would typically require higher activation energies, but in the mineral lattice, we might have hotspots that lower the barrier. Elena, nodding vigorously. Exactly. This is the kind of environment where quantum mechanical phenomena might tip the balance, especially under high pressure and in the presence of certain transition metals. They spoke for an hour, weaving quantum mechanics into the emergent replicative phenomena. James realized he needed Elena's expertise to refine the theoretical framework. If they could show a quantum tunneling pathway that made the formation of these replicating molecules inevitable under the right conditions, the discovery would be all the more powerful. Elena, let me run some quantum dynamics simulations on your system. I can use my lab's cluster at MIT. We'll see if we can replicate your data in a purely quantum mechanical model. James, that would be invaluable. Thank you. Eleanor left, leaving James staring at the half-empty coffee cup on his desk, feeling a swirl of excitement and dread. He typed a final note into his digital journal for the night. June 22nd, 11:12 p.m. We have strong indications of a replicating sulfur organic complex templated on iron-sulfur minerals. Collaborating with Dr. Kim for quantum simulations. Next steps: isolate the molecules, confirm replication off-surface, and carefully document all controls. This is beginning to feel real, both thrilling and terrifying. He closed his eyes, imagining the surge of controversy and wonder if this finding bore out. Inorganic matter, giving rise to self-replicating organic complexes. What would it mean for biology, philosophy, even religion? The puzzle was deepening, and James felt both detective and witness to something extraordinary. Episode 3. Threads of Skepticism. Skeptics arrive. The word had spread far beyond UCSD. A week after James's team first reported their data at an internal seminar, he found himself fielding emails from all over the world. Labs in Germany, Japan, and the UK wanted to know more. Some were supportive, others demanded to see raw data or replicate the findings themselves before believing a shred of it. The skepticism was understandable. Claims of creating or discovering self-replicating molecular systems from inorganic substrates had been around for decades, but none had been definitively validated. On a humid Thursday morning, James hosted a meeting with members of the UCSD biology department, as well as a panel of external experts. It was unusual for such a small lab group to draw so much attention, but the stakes were high. Present were Dr. Miguel Taveras, a well-known evolutionary biologist who had once done postdoctoral work on synthetic RNA replicators. Dr. Barbara Silverstein, a veteran molecular biologist with a reputation for ruthless peer review. Dr. Kang Liu, a geochemist from Caltech who specialized in early Earth conditions. They assembled around a long wooden conference table in the department's lounge. James used a projection screen to show his slides detailing the results, while his lab members piped in with comments. Miguel Taveras, leaning forward. This is remarkable, but I have to question the evidence for actual replication. So far, you've shown an increase in certain sulfur organic complexes, but how do we know it's templated rather than autocatalytic chemical cycling? James, good question. We ran control experiments without the mineral substrate, and also with chemically similar but structurally different minerals. Those control runs produced nowhere near the same level of molecular growth, nor did we see exponential increases over cycles. The replication phenomenon is unique to the iron-sulfur surfaces that have developed these new facets. Barbara Silverstein, eyes narrow. Have you purified these molecules and shown that they can replicate independently, maybe in solution with some catalyst? James, we're in the process of isolating them, but the data strongly suggests that the surface itself is acting as the catalyst and template. Off-surface, replication may not proceed the same way. Kang Liu, that might actually match the geology of early Earth. If replication first arose in specialized pockets, like iron-sulfur vents, then life was locally contained before eventually dispersing. However, the molecules that do replicate in your setup, do you have structural data on them? Sylvia, from across the table. We have partial data from X-ray absorption near-edge structure, XANES, and mass spectrometry. We're coordinating with Dr. Kim at MIT for more quantum-level details. But yes, we suspect these are organosulfur complexes with iron bridging units forming a semi-stable lattice. The discussion continued for hours, with Taveras and Silverstein raising repeated concerns. Could it be contamination? Are we sure about the stoichiometries? What about ephemeral radical species that vanish quickly? Finally, Taveras leaned back, folding his arms. Taveras, I still have reservations, but if you can replicate these findings in an independent lab with full controls, I'd be inclined to think there might be something genuinely new here. James nodded. He understood the necessity of independent replication. Science thrived on it. He promised to share protocols and samples once they had a stable supply of the replicating complexes. In many ways, this was a detective's final test of a clue. If others can't corroborate it, the clue might be nothing but a red herring. New twists from quantum physics. That evening, James got an email from Dr. Elena Kim at MIT. She had run her first quantum dynamics simulations, focusing on the electron tunneling aspects of the iron-sulfur surfaces. Her results were startling. From Elena Kim, MIT, to James Ocampo, UCSD. Subject: Preliminary tunneling simulations. James, I fed your data into our quantum molecular dynamics framework. The system shows strongly enhanced tunneling for carbon-sulfur and carbon-iron bond formations when the mineral surface is in a specific electronic state. Interestingly, the surface's electronic state locks in after a few cycles, effectively lowering the activation barriers even further in subsequent generations. This might explain the exponential replication. Each new cycle, the surface is more primed for binding. We're also seeing resonant electron delocalization across the surface, reminiscent of topological insulators, albeit on a microscale. Could we be looking at a proto-biological quantum effect? Let's talk soon. Elena. James read and reread the message, heart pounding. The mention of proto-biological quantum effect made his mind swirl with possibilities. All living systems rely on quantum phenomena in some capacity, especially in enzyme catalysis or photosynthesis. But if the inorganic substrate itself was harnessing and optimizing a quantum effect to assist replication, that was a leap into new conceptual territory. It suggested that this bridging between inorganic and organic might be an inherent property of the right kind of matter under the right conditions, almost inevitable if nature had enough time. Confrontation with doubt. Amid the excitement, James wrestled with doubt. Scientific history was littered with grand claims that collapsed under scrutiny. He spent a long night in the lab's darkened corridor, watching the reactor hum behind reinforced glass. The swirling fluids within looked like a miniature undersea vent, a hidden cauldron forging the building blocks of life. He couldn't help but think of Darwin's Warm Little Pond, or Haldane's Primordial Soup, updated to the 21st century with high-pressure lines and advanced AI analytics. Was this a fleeting artifact or something truly monumental? At around midnight, he called his graduate student Chris, who lived off campus. James, on the phone. Chris, sorry to call so late. I need you to run one more check on the reactor logs. Something's nagging me about the baseline for each cycle. Could you forward me the raw data? Chris, yawning. Sure, Doctor. Ocampo. But everything was stable when we left. Any particular concern? James. I just want to see if there's a drift in calibration that we missed. If the baseline is shifting, it might artificially inflate the replication numbers. Chris. I'll send it in 5 minutes. James opened the data as soon as it arrived and cross-correlated it with the original. No, there was no drift. The baseline was rock solid. The replication effect was real. He exhaled, letting relief wash over him, but also feeling the weight of responsibility intensify. Espionage. A new, unexpected twist emerged the following day. Rena, one of James's grad students, noticed that some of their lab's data logs were accessed from an unauthorized IP address. The system had flagged the intrusion automatically. Rena, alerting James, I think someone is snooping on our servers. This IP belongs to a domain in Switzerland, but it's masked. They downloaded some logs from last week's experiments. James, who would do that? Another lab? A corporate interest? This research could be worth a fortune if it leads to new biochemical or quantum technologies. Rena, I've changed the passwords and restricted access. Should we report this to the university's IT department? James. Yes, do that immediately. And keep an eye on any unusual activity. Also, update the backups offline. This intrusion added a cloak and dagger dimension to James's detective saga. If the data was as revolutionary as he feared it might be, corporate or even governmental interests could be prowling around. The stakes had risen. It wasn't just scientific curiosity on the line. It was potential intellectual property with world-altering implications. James also realized he needed to accelerate the process of peer-reviewed publication. The best defense against data theft or overshadowing was open, transparent science. But he also worried, what if we're not ready? What if there's a flaw we haven't caught? Still, he initiated the earliest steps, drafting a manuscript to share with colleagues for feedback. The cat was out of the bag, whether he liked it or not. An unexpected ally. The next afternoon, James received a call from Dr. Aditi Rao, a Nobel Prize-winning chemist from Stanford. Her voice crackled with enthusiasm. Aditi, James, I've reviewed what Tavera sent me about your results. If these replicating molecules are real, we may finally have a testable laboratory platform for the origin of life scenario. Imagine being able to watch natural selection happen on an inorganic substrate. James, that's my dream scenario, but we're still verifying, step by step. I'd love any insights you have on controlling for contamination or novel reaction pathways. Aditi, I have a technique we developed for single-molecule spectroscopy. We could see, in real time, how these molecules bind and replicate. If you let me collaborate, I can send a team with the equipment to set up in your lab. James's initial reluctance to bring in too many outside groups wavered. If Dr. Rao, a world-renowned chemist, wanted to collaborate, it might lend invaluable credibility to the research. James, that would be incredible. Let's do it. This discovery belongs to the community. They agreed on a timeline. 2 weeks later, her team would arrive with specialized single-molecule detection apparatus. Part of James was excited, part anxious. The more eyes on the data, the more robust the findings, but also the more intense the scrutiny. The story was escalating, turning from a quiet lab result into a global scientific pursuit. Nightfall reflections. Late that evening, James found himself in the empty conference room, the city lights twinkling beyond the glass windows. The silhouette of the La Jolla coastline framed the horizon. He thought of the intrusion, the potential replicators, and the swirl of attention from the scientific community. He picked up his personal notebook, a relic from a simpler time, when pen and paper were enough. He sketched a crude diagram of the iron-sulfur surface with repeating lines representing the organic complexes, each generation doubling across the substrate. Below it, he wrote, "We are on the brink of demonstrating how non-life might turn into life. This challenges our entire worldview. Where do we draw the line between dead matter and alive matter? Does life spontaneously erupt when complexity crosses a certain threshold, or is it inherent in the quantum properties of matter?" He closed the book, switched off the lights, and walked down the empty hallway. Tomorrow, he thought, the next round of tests begins. Like a detective following the next clue, he was driven by an insatiable need to know the truth, whatever it might be. Episode 4. Crossroads of doubt and wonder, pinpointing contamination risks. The UCSD lab was abuzz with activity. Word of Dr. Aditi Rao's impending visit circulated, raising the stakes for James and his team to deliver clean, indisputable results. Over the past week, they'd redesigned the experimental setup with a series of contamination safeguards. Sterile enclosures. The flow reactor was housed in a biosafety cabinet to minimize any stray microbial intrusion that might confuse the data. Triple distilled water. They used ultra-pure water to ensure no background organics. Blank mineral controls. They introduced identical minerals but pre-treated to remove reactive sites. labeling with isotopes. They planned to use isotopically labeled carbon-13 and sulfur-34 to track the molecular origin of any newly formed organics. James spent his days running validation tests and nights analyzing data. The results remained consistent. In the presence of the active iron-sulfur minerals, a new generation of molecules appeared each cycle, doubling or near doubling in quantity. The control experiments yielded no such phenomenon. Dialogues with skeptics. While the intralab mood was cautiously optimistic, external skeptics multiplied. James found himself repeatedly on Zoom calls with critics, some well-meaning, some openly hostile. Dr. Kevin Rosenthal, Oxford University, in a pointed tone. Extraordinary claims require extraordinary evidence. How do you exclude the possibility of pre-existing biological material in your lab or the samples? James, we've gone through extensive sterilization, used isotopically labeled feedstocks to demonstrate the newly synthesized molecules incorporate labeled atoms only found in the experimental medium. No pre-existing biological source can explain that. Rosenthal, that's promising, but not conclusive. I'll wait for the peer-reviewed publication. Some calls took a more philosophical turn. Dr. Amira Bhatt, Philosophy of Science, UC Berkeley. If your findings hold, it suggests matter itself holds the potential for life under the right conditions. That might undermine centuries of the mind-matter duality. Do you see ramifications for how we define consciousness? James often sidestepped philosophical tangents, focusing on the science, but deep down he felt them. If life can spontaneously emerge from the quantum interplay of inorganic surfaces, what else might nature do when given enough time? Breakthrough in single-molecule imaging. Finally, Dr. Aditi Rao arrived with her postdoctoral fellow, Dr. Nadia Hussain, and a moving truck full of specialized single-molecule detection equipment. Installing it in James's lab took 2 days. They used a technique combining total internal reflection fluorescence microscopy with specialized fluorophores that could bind selectively to the new molecules as they formed. The moment of truth came when they introduced the labeled feedstocks into the reactor, let the reaction proceed, and then piped a small aliquot into a microfluidic chip on the TIRF microscope stage. If the molecules had formed and replicated, they'd glow green as they bound the fluorophores. James, Aditi, and the entire lab held their breath as the first test ran. On the monitor, tiny green dots began to appear, then multiply. Aditi, eyes glued to the screen. That's replication in real time. Each dot corresponds to a molecular complex with the fluorophore. Now watch, some of them are splitting, forming 2 distinct dots. James, it's not standard cell division, of course, but a templating effect at the molecular scale. Rena, softly. Incredible. It's exactly what we hoped to see. They recorded hours of video footage, capturing the replicative events. This was the closest thing to direct visual proof that under the right conditions, inorganic catalyzed molecular replication was real. A hush fell over the lab, punctuated by hushed exclamations as the data poured in. A growing rumble of implications. The next day, at a departmental colloquium, Dr. Rao presented preliminary findings to a standing room-only crowd. Skeptics filled the front row. She was a commanding presence, explaining in precise detail the experimental controls, the TIRF imaging, and the isotopic labeling. By the end, a buzzing sense of awe overtook the auditorium. Dr. Rao, concluding, while we must remain cautious, the evidence strongly indicates templated replication. If further corroborated, this work not only enlightens our understanding of life's origins, but also raises the possibility that life might emerge wherever similar conditions exist, even on other planets with iron-rich surfaces. The audience erupted in applause and a flurry of questions. Even the skeptics seemed subdued. Miguel Taveras later pulled James aside. Taveras, this is extraordinary. If it holds up, it's the biggest leap in origin of life studies since the Miller-Urey experiment. Congratulations. James nodded, feeling a mixture of pride and an undertow of anxiety. Be rigorous, be thorough, he reminded himself. The next step was drafting a paper for Nature or Science, detailing every procedure. A mysterious message. That evening, James discovered an anonymous email in his inbox. Subject: You are treading on volatile ground. Body: Dr. Ocampo, your findings could reshape humanity's self-conception. Be wary of releasing details prematurely. There are forces that benefit from the status quo. A friend. James's pulse quickened. The intrusion, the corporate or governmental interests. Were they trying to warn him or threaten him? He frowned, reread the cryptic message, and then deleted it. He resolved to double down on transparency. Sunlight is the best disinfectant. If this discovery truly was groundbreaking, the entire scientific community needed to see it. Quantum revelations. A phone call from Dr. Eleanor Kim arrived the next morning. Elena, voice animated. We found something astounding in our advanced simulations. The mineral lattice system exhibits a phenomenon akin to a quantum ratchet, where energy fluctuations drive the reaction direction preferentially toward replication. It's a subtle interplay of electron wave functions. And get this, once the complex forms, it stabilizes the mineral's electronic structure for the next cycle. It's a feedback loop. James: You mean the presence of these replicating molecules modifies the substrate's quantum state in a way that fosters more replication? Eleanor: Exactly. It's co-evolution. Mineral and molecules shape each other. In essence, the boundary between inorganic and organic is blurring at the quantum level. James sat down, letting the gravity of her words sink in. If the substrate and molecules co-evolved in synergy, it implied a fundamental continuity between lifeless matter and living processes. Life's emergence might be less a random fluke and more an inevitable progression, given the right environmental scaffolding. James, quietly: This changes everything. The pressures of publication. By the end of the week, the lab had accumulated enough data to start drafting a landmark paper. The authors included James, Sylvia, Chandler, Maya, Reena, Chris, Elena Kim, Aditi Rao, and Nadia Hussain, a cross-disciplinary powerhouse. Drafting was a painstaking process, every statement requiring bulletproof evidence. Figures showed real-time replication curves, spectral data confirming molecular structures, and quantum simulations illustrating the ratchet effect. Yet James worried about potential pushback. James, in a team meeting: We know critics will comb through every line, looking for weaknesses. Let's be sure about what we claim and what we leave as open questions. Aditi: Yes. We claim we've observed inorganic templated replication with organosulfur complexes. We do not claim these molecules constitute life in the full sense. That's for further study. Chandler, cautiously: And we should consider the potential implications. If replication is so readily achieved, perhaps it's not a unique Earth-based phenomenon. That's an exciting speculation, but we should label it as such. James nodded, thankful for the balanced approach. By the following Monday, they submitted the paper to Nature, attaching all raw data in supplementary materials for transparency. A hush of anticipation descended on the group. The next steps were peer review, potential revisions, and, if accepted, a seismic shift in origin of life research. A glimpse of the moral and existential. One night, after the submission, James took a long walk on the beach near La Jolla. The waves crashed rhythmically under a sky strewn with stars. He couldn't help but think of how many worlds might exist in our universe, each with iron-laden minerals, hydrogen sulfide vents, and the potential to cross that invisible barrier into organic complexity. What does it mean for our understanding of ourselves? Humans had always wrestled with the idea that we might be just cosmic accidents. If quantum ratchet effects in minerals make life's emergence more of an inevitability, then perhaps the cosmos teems with biology in myriad forms. Are we alone? Almost certainly not. That realization carried both wonder and a touch of existential vertigo. He stooped to pick up a small pebble washed ashore, smooth and dark under the moonlight. Could it be that in some primordial ocean, matter like this had sparked the first building blocks of consciousness? He felt a certain humility and awe. No matter the accolades or controversies ahead, the truth is bigger than me. He smiled softly, letting the ocean wind rustle his hair. Let the detective story continue. The clues are everywhere. Episode 5. Storm of Controversy. Early reactions and media frenzy. Within days of the preprint publication, the paper was posted online for open review while Nature deliberated. Social media exploded. Headlines shouted, "Scientists discover possible origin of life," and "Inorganic matter learns to replicate." Groundbreaking research at UCSD. Journalists clamored for interviews. Pop science blogs declared it the final nail in creationist coffins, or proof of cosmic life inevitability. Religious groups took varied stances, some applauding the research as insight into divine creation, others condemning it as heresy. James found himself thrust into a spotlight he neither wanted nor expected. He tried to keep the discourse grounded. James, in a televised interview, "We haven't created fully living systems. We've observed templated replication at a molecular level, facilitated by iron-sulfur minerals. It's a critical piece in the puzzle of how life might have originated, but we're far from replicating the complexity of even the simplest cell." Despite his measured tone, sensationalism ran wild. Publishers wanted book deals. Tech companies offered R&D funding. Venture capitalists sniffed out potential applications in nanotechnology or advanced materials. James's inbox overflowed, forcing him to hire a part-time administrative assistant. Confrontation with religious scholars. A local interfaith council invited James to speak. Intrigued by the philosophical dimension, he agreed. On a bright Sunday afternoon, he entered a community hall lined with chairs, a small podium at the front. The audience included priests, rabbis, imams, and spiritual seekers of all stripes. James, at the podium, "I'm honored to be here. I want to clarify that our research is a scientific inquiry into the origin of life's building blocks. Many of you might ask, where does God fit into this? Science can't answer that directly. We're describing mechanisms, not ultimate meaning." Reverend Parker, from the front row. "Is it fair to say your work suggests life is a natural outcome of the laws of physics and chemistry?" James: "Yes, that's one interpretation. Another is that such laws are themselves part of a divine design. Science doesn't negate faith. It provides a way to understand how the universe might operate at a fundamental level." A respectful exchange followed, most attendees seemingly open to the idea that discovering the mechanism behind life's emergence didn't necessarily erase its wonder or spiritual significance. James left the hall feeling oddly uplifted. Perhaps bridging science and spirituality is possible, at least in some circles. Dark undercurrents. Yet not all reactions were so cordial. Anonymous threats and warnings continued. A suspicious black SUV was seen idling outside James's home. The university's IT department reported repeated hacking attempts on the lab's servers. While campus security assured him of protection, the tension weighed heavily. Sylvia, concerned: "You should stay vigilant, James. Not everyone welcomes a discovery that could shift power balances, be it religious, economic, or otherwise." James: "I know. But what can I do? Hide the results? That goes against every principle of science." He decided to press on, trusting that openness would ultimately prove safer than secrecy. Peer review battle. Meanwhile, the Nature review process began. The manuscript returned with a barrage of reviewer comments, some supportive, some scathing. Reviewer number 1 praised the methodological rigor, suggesting minor clarifications. Reviewer number 2 demanded additional control experiments to unequivocally rule out unknown microbial contamination. Reviewer number 3 was highly critical, accusing the authors of overinterpretation and prematurely concluding replicative behavior. James convened the entire team to craft a response. They agreed to run additional experiments, including advanced genomic assays to prove no extant microbes were at play. They also repeated the experiments in a sealed environment with heavy antibiotics and antifungals, just to be absolutely sure. The molecules still replicated. James, exasperated, speaking to the team. Reviewer number 3 wants definitive proof that no living organism, bacterial or otherwise, is meddling. Fine. We'll radio-sterilize every component and set up the experiment again with a triple check. They can't argue with that. Aditi, we should also refine our language. Instead of saying replication outright, let's use templated molecular duplication. That might appease conservative reviewers. They made the revisions, resubmitted, and braced for another round. The detective story's tension rose, with peer reviewers acting as the meticulous, critical eyes looking for any hole in the narrative. Internal tensions. Underneath the collaborative facade, cracks began to form. The stress of perpetual scrutiny wore down relationships in the lab. Chandler, who was always a skeptic, grew paranoid about overshadowing or about the possibility that they'd missed a crucial control. Chandler, late one evening, cornering James. Are we absolutely sure? I'm worried we're pushing a narrative too hard. The last set of experiments, did we run them with an inert substitute for the iron-sulfur? One that's physically identical, but chemically inert. James, we did, but I'll run it again, if it eases your mind. Sylvia, for her part, started fighting with Maya over the proper interpretation of XRD data. Eleanor, still at MIT, was occasionally at odds with Aditi over how to incorporate quantum tunneling theories into the final analysis. James found himself moderating small disputes daily, each one a microcosm of the bigger scientific debate. So many brilliant minds, each with a unique perspective and ego. He reminded himself this was normal in groundbreaking research. A window into alien life. Amid the chaos, a surprising letter arrived from NASA's Astrobiology Institute. They wanted to discuss the potential for replicating minerals on Mars or Europa, citing new findings of iron-sulfur deposits on the Martian surface. Dr. Harriet Long, NASA Astrobiology. Your results might be directly testable on the Martian regolith. If we find similar mineral lattice conditions there, we could see if the same phenomenon occurs. James felt a renewed surge of excitement. If the replicate on inorganic substrate phenomenon occurred off Earth, it would provide near irrefutable evidence that lifelike processes are not unique here. That would be the ultimate detective clue, a second case of the same phenomenon, beyond Earth. He immediately agreed to share protocols. Public lecture and the crescendo. That weekend, James was slated to deliver a public lecture at UCSD's largest auditorium. Over 1,000 people attended, students, faculty, citizens of San Diego, and beyond. The line snaked outside the building. Taking the podium, James gazed at the sea of faces. He saw curiosity, hope, doubt, even fear. This moment is about more than just the science. It's about the story of who we are. James, projecting calmly, we found something remarkable. Under conditions that mimic early Earth hydrothermal vents, iron-sulfur minerals contemplate the assembly of complex organosulfur molecules. These molecules display a form of replication, doubling or near-doubling each generation. This isn't life in the full sense we know it, but it may be a key step toward life's emergence. He showed images of the TIRF microscopy, the electron micrographs, the quantum simulations. The audience sat in rapt silence, punctuated by gasps at key revelations. James, what does this mean? It suggests that the boundary between inorganic and organic might be more permeable than we ever imagined. Life might not be a cosmic accident, but a natural progression governed by quantum chemistry, thermodynamics, and time. This new understanding has deep implications: scientific, philosophical, and even spiritual. We stand on the cusp of rewriting our narrative about how we came to be. Applause thundered, and a half-dozen hands shot up for questions. Some were starry-eyed, others challenging. James did his best to answer patiently and honestly. He felt something shift in the room, a collective sense that they were witnessing history. Yet amid the triumphant mood, James spotted a figure in the back, arms crossed, face obscured by a cap. The figure shook their head slowly and turned to leave. A chill ran down James's spine. There were corners of this world, he realized, that did not want this discovery to gain traction. But it's too late, he thought. The genie is out of the bottle. Episode 6. The Unraveling and the Dawn. Acceptance and the Big Reveal. A month passed. The final word came from Nature, accepted with major revisions. The editorial board insisted on cautious language and demanded a full suite of contamination controls as supplementary material. James and the team were jubilant nonetheless. This was a near unprecedented endorsement for such a transformative claim. On the day the acceptance news broke, mainstream media outlets ran headlines like "Mystery of Life's Origins Solved." The university scheduled a press conference with James and Chancellor Johnson, who publicly lauded the research as a milestone for UCSD. That morning, James found a note on his desk, unsigned, typewritten on plain paper. "Congratulations on your success, Dr. Ocampo. We hope you wield this knowledge responsibly. Some truths, once revealed, can't be taken back." He pocketed the note, uncertain whether it was a threat, a warning, or a genuine congratulations. Either way, he had no intention of hiding the findings. Detective meets the grand mystery. As the publication date neared, reporters called James a science detective, a moniker that both flattered and amused him. In a final flourish of thoroughness, James reran the critical experiments. The results matched perfectly. The replicating molecules were real, stable, and unstoppable once the right conditions were in place. He sat at his desk, reflecting on the journey, like a detective piecing together a cosmic crime scene. Clues were the catalytic surfaces and new spectral signatures. Suspects included contamination or measurement error. Witnesses were the advanced AI simulations, TIRF microscopy, and quantum analyses. Verdict: inorganic matter can, under the right conditions, transition into self-replicating organic structures. Global scientific community reacts. Once the paper formally appeared in Nature, the global scientific reaction was swift. Synthetic biologists launched projects to adapt the replicating molecules for nanotechnology. Geochemists re-examined old data from deep-sea vents, searching for evidence they'd overlooked. Philosophers penned essays on the blurred line between living and non-living. Spiritual leaders debated how this discovery fit into divine creation narratives. James participated in an online conference with some of the biggest names in science. Moderator, excitedly: "We have Dr. James Ocampo, whose lab just published the famed iron-sulfur replication study. Dr. Ocampo, do you believe life might exist wherever such minerals are found, like on Enceladus or Titan?" James: "The data suggests that if similar conditions exist, liquid water, iron-sulfur minerals, a source of energy, and time, then yes, self-replicating processes may emerge. Whether it leads to complex life is another leap entirely, but the door is opened." The global conversation turned to the inevitability of life, with James at its epicenter. Confronting the ultimate questions. Late one night, James had a private video call with Elena Kim, who was finalizing some more quantum simulations. They were both exhausted but giddy with the pace of discoveries. Eleanor: "We're seeing that once the replicators form, they can evolve. Introducing random variations in the reaction mix leads to structural analogues that might have different replication rates." James, rubbing his temples: It's natural selection at the molecular level. We might be witnessing the earliest form of Darwinian evolution, pre-RNA, purely inorganic-organic synergy." Elena: "Exactly. With enough cycles, we see a small fraction of the molecules replicating faster or binding more strongly to the mineral. They outcompete the original variants." James had no words. The detective puzzle was morphing into a grand tapestry of emergent complexity. If these molecules could mutate and evolve, the step to a full-fledged living system might be more of a continuum than a sudden threshold. A final threat and resolution. The last confrontation happened quietly. After a day of back-to-back meetings, James exited the biology building to find a stranger waiting near his car, a tall, broad-shouldered man in a dark jacket. "Stranger," voice low, "you've made quite the splash. Not everyone's happy about it." James, heart pounding: "Who are you?" Stranger: "A concerned party. Some powerful interests don't want the notion that life emerges naturally from matter. It upsets certain economic and ideological structures. There's talk of cutting your funding, or worse, discrediting your lab." James swallowed. He had half a mind to call campus security, but the man turned away and walked off into the darkness. A final ghost, James thought, the last echo of fear. He resolved to stand firm. The data was public. The research was published. No intimidation could roll back the tide of knowledge. Epilogue: The New Dawn. Weeks later, James found himself at a quiet cafe overlooking the Pacific Ocean. Life had settled into a new normal: constant interviews, huge interest in the lab's next steps, but also a sense of relief that the core discovery was now safely in the scientific record. He reread a section of the Nature paper, the lines that captured years of labor. "Our results demonstrate that under conditions mimicking early Earth hydrothermal vents, iron-sulfur minerals can facilitate the assembly of novel organo-sulfur complexes exhibiting templated molecular duplication. This phenomenon underscores the plausibility of inorganic to organic transition processes that may have preceded the emergence of fully autonomous life." He closed his laptop and gazed at the horizon. A small group of dolphins breached the waves, their sleek forms glinting under the sun. Life, he mused, so abundant now on Earth, might have begun in such a simple, almost humble way. Atomic bonds forming on mineral surfaces in the ancient ocean, forging the path to consciousness. The detective story had reached its final act, yet the real mystery was ongoing. How far did this continuum extend across the cosmos? Could there be countless worlds where stony substrates cradle the seeds of life, waiting for a spark of quantum synergy? With a smile, James raised his coffee mug in a silent toast to the iron-sulfur complexes that had begun it all. In the end, we are the products of stardust and quantum chance, shaped by eons of evolution, and our place in the universe feels both humbled and enriched by the knowledge that matter itself, under the right conditions, can write the earliest lines of life's grand script. He took a deep breath of salty air, feeling more alive than ever. The boundary between inorganic and organic wasn't a chasm, it was a continuum, pregnant with possibility. In that revelation, James saw not just a scientific breakthrough, but a profound reminder that creation is woven into the fabric of reality, shimmering in every atom and every photon, waiting, like a detective's clue, to be discovered.